Welcome to another Macron Group webinar. My name is Charles Zona, and today our presenter is Bill Chapin. Bill is going to talk to us about meaningful particle analysis and how it all begins with the light microscope, in particular, the use of the stereomicroscope. Before we get started, I would like to talk a bit about Bill's background. Bill is a senior research microscopist at Macron Associates with over 40 years of experience in trace evidence and particle identification. Prior to coming to Macron, Bill spent over 20 years at the Johnson County Crime Lab in their trace evidence section. Bill has taught a variety of courses at Hooke College of Applied Sciences, including Advanced Polarized Light Microscopy, Introduction to Forensic Trace Evidence, and Pharmaceutical Materials and Contaminants Identification. Bill will field questions from the audience immediately following today's presentation. This webinar is being recorded and will be available on the Macron Group website under the Webinars tab. And now, I will hand the program over to Bill.
Hello. I just took a look at some of the names here on the attendee roster and see a lot of people that I know, and that puts me at ease because I'm doing this live and I was a little afraid I was going to freak out. Anyhow, again, my name is Bill Chapin, and I have been working with light microscopy for decades, actually, and any of you that know me know that that's my go-to device. I really think that there are a lot of people out there in industry that are not utilizing the light microscope as much as it could be. I think it lends itself to a lot of improved analyses and a lot better sample preps. If you've got any questions as I'm talking, go ahead and type them in. We'll see them here. If it's something relevant to what I'm speaking about at the time, I'll try to take those questions and answer them on the fly. We're going to start out by talking about some equipment and tools. We're going to talk about the stereomicroscope, the polarized light microscope, illumination techniques. We're going to spend quite a bit of time talking about and emphasizing illumination techniques. Too many techniques are not taken advantage of, so that we lose some effectiveness of our microscope. And finally, we're going to talk about a few sample handling tools, because it requires a different toolbox than if you're using macroscopic techniques. I'm going to then go into a half or more of the discussion. I'm going to show you some times when the light microscope can actually make identifications where other instrumental techniques may not. And we're going to spend a lot of time with sample preparation under the stereoscope. We're going to create a homogeneous sample from a heterogeneous material and do some other kind of fun things. I want to point out that the examples I'm using should be thought of as springboards for other similar analyses. For instance, when I'm talking about cross-sections of paint, some of you may want to talk about or be thinking about cross-sections of plastics or some other material. When I'm talking about surface texture of paint or surface texture of plastics, there may be some metals applications where you're wanting to look at surface texture. So try to take my techniques and apply them to your areas of interest. Standard stereomicroscope. I say standard. It's not really standard. It's a very beefed up microscope. It's basically no different than what you used in high school biology or perhaps biology or entomology in college, but we've added a lot of things to it. Let me get my little laser pointer here. We've added multiple light sources, illumination sources, and we've added some additional filters to it. I've got two objectives. I've got a 1.x objective and a 0.5 objective, and we've got a port up here for a camera. So in my opinion, this is really what's necessary to really optimally use a stereomicroscope. The other scope we're going to talk about is a polarized light microscope. Many of you are familiar with that. I say it has set magnifications. Its magnification is dependent solely on the objectives and the eyepieces. You can buy several nose pieces and put up to 6 objectives on a nose piece. Typically, you're going to have a 40x objective, or excuse me, a 4x objective, a 10x objective, maybe a 20x, maybe a 40x, so that you can go up to 400x magnification. 500x is nice if you're wanting to look at interference figures. We're not going to go into that today, but it's a nice use for that because of the higher numerical aperture. And in my application here, there are times when I need to look at bacteria, so we have 100x objectives so that we can go to 1000x magnification with immersion oil. The stereoscope is somewhat different in that it has a zoom magnification range on it. Lower magnification, 5 or 10x to 100 to maybe 135x, that's zoomed on this dial here. It's also, the better scopes will have a click on or click off device here. That's useful if you're going to take photomicrographs and put scale bars in, because it will click and lock into certain magnifications instead of you having to guess on a sliding scale where you are, so that you can make sure you've got the right kind of magnification. Oblique illumination. It's most commonly thought of in conjunction with a stereoscope. The light comes from the side. You can see here I've got 2 bifurcated light sources that I can change the angles. Sometimes I want just very severe raking light. If I'm looking for colorless fibers on a filter, I want to bring that arm down and use severe raking light. On something else, I may want to pull that up and bring it more directly down from the top. Another adaptation to this is that you can take on either objective in this location, and you can put a ring light. It's got some limited uses. When it's useful, it's great. Sometimes it just doesn't do a thing for you, so you just get rid of it. What we often forget is that on a polarized light microscope, oblique illumination is also very useful. When you're looking at color, maybe you've got a fugitive dust or a dirt sample, and it's got various different kinds of paint in it, or it's got some white spheres and some black spheres, things like that. Through the oblique illumination, you can see that color, and you can learn a whole lot more about your sample. Now, when we go to transmission illumination, that's typically what we think of on a polarized light microscope. The light comes up through the bottom, comes up through our specimen, and the light comes on up, and we see it through the eyepieces. So it's transmitted. It goes through the specimen. One thing that people often forget is that this kind of light will change the color of some things, particularly when you have fibers. You may look at it and oblique illumination, and it's a purple fiber, and with transmitted illumination, it may be more pink, or it may be more maroon. It's going to have a color shift to it because of the way the light's transmitted through it. Some people, but not a lot, do not recognize the value of transmitted light on a stereomicroscope. I think it's invaluable. It's exactly the same concept. The light comes up from the bottom through your sample and up to your eyepieces. It's useful particularly if you're looking through a medical bag for particulate, so to speak, like an IV bag or something, through a vial, things like that, where you're hunting free-floating particulate. You can see it much better that way oftentimes than you can with oblique illumination. What I would submit to you is that we can take the stereoscope further and really enhance that transmitted illumination. What I will do is I will take and drop a polarizer right here. And so we've got transmitted polarized light just like we do over here in the Polscope. Now it becomes a little different. This is a quarter wave plate that is in place when we do coaxial illumination, which I'll talk about next. But it's something that's already on the microscope, so you may as well take advantage of it. Now when you look at your sample, you can get a partially cross-polarized illumination system so that you can still see birefringence, some different lighting effects on those particles. Let's say you're looking at a soil sample and you're trying to find glass. You can very easily use this to locate the isotropic glass particles and separate them from the anisotropic quartz particles. So your quarter wave plate acts like your traditional analyzer in the Polscope, but it's a pseudo cross-polarization technique. So it doesn't have the quantification, I guess you would say, that you would see on the Polscope. Now we go to reflection techniques, the most underused and most powerful technique, particularly for pharmaceuticals, that you really need to look at getting. In reflection, it's different from oblique in that it comes straight down from the top, hits your sample, and bounces back up and then to your eyes. Same way with the Polscope. It comes from the top, down, and back up. So it's a reflection technique from the surface. When you're dealing with a stereomicroscope, it's called coaxial, basically because there are two different light axes in the stereoscope. The episcopic, or in the polarized light microscope, you have a single light axis. So it's episcopic, is what they call it. There's some technical differences in how they create the effect of what you see, but they both produce exactly the same observation of materials. We're going to take a look at the critical use of that, and I will say that there virtually is never a sample that I don't use coaxial or episcopic illumination on. But we'll see some of those here in a minute in some of my samples that I'm going to show you. Let's talk about our toolbox. Down here in the lower left is an array of tools that I'm going to be using in this presentation. We've got a tungsten carbide scribe here. We've got a micro-scalpel. We've got 3 tungsten needles, and I've got 2 sets of tweezers. One is curved, one is straight. These tweezers are commonly referred to as Dumont type. That's D-U-M-O-N-T. They're very fragile. You drop them once and you throw them away. I generally buy them in multiples so that I've always got a good set of tweezers at hand. These tungsten needles are shown up here in the upper left. And we make our own, but you can purchase them pre-made. You need all kinds of different tungsten needles for different applications. These are coarse tungsten needles. Later on in my videos, when I'm removing a blue particle from a tablet, I'll be using one of these coarse needles. At other times, I will be picking up small particles with this medium needle. I personally very seldom use a fine needle because I'm too heavy-handed and I bend it. But you may be able to use that, and there's certainly some applications that would make life easier. You can make these angled. You can make hooks on them. We've made some that actually are scoops, almost like a mini spatula. So you can do all kinds of things once you learn the techniques. I can stop here for a minute and tell you that if you go into the Macron website, you can find short presentations and articles on how to create tungsten needles. The same thing here with the micro pipettes, and also when we get down here to talking about the micro glass slides. Can't sit here and tell you right now exactly how to get there, but go poking around our website and you'll find those. If you can't find them, let me know and I'll send you some information. This is another invaluable tool. No longer can you use a pass-through pipette. You can't even use a plastic transfer pipette. You've got to go much smaller than that. This is a pipette that you use on just a standard pipetter. This is it's actually an electronics bulb. You can get that at auto parts stores. It fits right on the end of that pipette tip. You put a hole in this end, and then when the open end is placed in liquid, it draws liquid up by capillary action. When you then touch this tip onto a flat surface, that liquid flows out by capillary action. Again, you'll see me doing that here in a little bit. These tips are generally going to deliver less than a microliter. Sometimes that's 10 times too much. So you can take this tip, heat it, pull it so that it stretches, and then cut it off so that the inner diameter is smaller, and then you can get down to about 50 nanoliters of liquid delivery. And sometimes that's necessary. Another invaluable piece of equipment are these glass slides that we make. We just take a standard cover slip, score it into, 1 to 4 millimeter squares using a tungsten carbide scribe. Then we break those and rinse them in ethanol to get rid of the glass chat or small particles, and create these and then store them in a Petri slide. These are useful for two things. First of all, they're useful if you've got a 100 or a 200 micrometer sized particle that you want to look at by polarized light microscopy. It's a whole lot easier to find that particle under a 4 by 4 millimeter cover slip than it is under an 18 by 18 millimeter cover slip. So it saves search time. It also can save on the amount of the volume of solvent or liquid that you have to use. The other thing, you're going to see me use it as a press. When I make my infrared preparations, you'll see me using a glass slide like that. There's also, you can make them larger. These are 5 to 7 millimeter square slides are nice when you've got a 500, 750 micrometer size particle that you want to work with. Let's take a little closer look at a couple of tools. One is, the next one we're going to look at is this Micro-scalpel. This is a slightly different one. This is has a disposable tip on it. You buy the handle and then you buy the tips, and the plastic screws into this handle. Now these are ophthalmic surgery handles or microscopes. They're available through Surgistar, and you can get several different types. This is a 45-degree angle, and I know you can get them in 15s. I happen to like the 45 myself. You can also get them with shaft length differences. This is the smallest one we can get, and that's this dimension right here. If you get it much longer, you might be able to access some particles more easily, but the scalpel blade is going to break much more easily. So I like to get the shortest one that I can find. You'll see me using that later. This is one of the most controversial tools, if you will, in the Macron building. It's a roller tool. You either absolutely love it or you absolutely hate it. I absolutely love it. I use it on lots and lots of samples. It's primarily used to flatten particles. If you've got a big piece of plastic, maybe a millimeter thick or even a 200 micrometers thick, that's way too thick for infrared. It's very difficult sometimes to slice off a shaving. So you take a small particle off, you roll it with this, much like you're using a rolling pin on pie dough or biscuits. So we'll show you the use of that. The one reason people don't like it is that there are times when your particle will stick to the roller. For me, that's not an issue. I just simply change the focus of my microscope, roll this up where I can see it, take my tungsten needle, pull that particle off, and go on down the road. It doesn't bother me at all. So you can pick your poison on that one. The vast majority of work that we do here on all of our small particles is done by transmission Micro-FTIR. We make our own KBR plates. That's what you're looking at here. We buy large blocks of KBR, and they're cleaved. I believe the instructions for this is also on the website. They're 1 to 2 millimeters thick. This plate happens to be about 4 millimeters wide by 9 millimeters long. That's just a function of how your crystal cleaves and being large enough to span your sampling device. So what you're looking at here, you've got a microscope slide that actually extends both ways off the screen. I've added up here a small piece of double-sided tape. Then I've taken my KBR plate and I've laid it over top of that at the edge to secure it when you're actually mounting your particles. And you'll see me mount some particles later. When we do EDS work, we use a beryllium stub. I need to throw in here that beryllium is carcinogenic in powder form. We know how to handle it. We also we don't create a lot of, we don't sand them or anything here. We send them out to be polished. So they're relatively benign for our use. Here on the left, you're seeing at a lower magnification a beryllium stub that is prescribed into approximately 1 millimeter squares, and you've got a location grid on it. This is exactly the same stub. I've doubled my magnification, but this is with coaxial illumination. Much, much easier to see what you're doing here than it is over here in ring or oblique illumination. We do not use carbon tape or carbon tabs very often. Typically, our particles are 50 micrometers or less. Particles of that size will sink down into the adhesive, and sometimes when it gets into the chamber and you add your beam heat to it, that adhesive will melt and that particle will sag. So we don't use those except for very large particles. Now, let's talk about the power of coaxial illumination. What you're looking at here is a field of view on a polycarbonate filter. I will tell you that there is tons and tons of glass delamination flakes on that filter. You can't see them. However, if we change over and use coaxial illumination, that's what shows up. That is the exact field of view. You can see here these white particles are actually these two black ones here. Over here is a white particle, is that black particle. You've got this one, which is this one, which shows it's the same field of view. So these are all thin glass flakes of delamination. They're probably 50 nanometers thick, if that. What you're also seeing here for a different application is you're seeing very shallow striations on the surface of the filter. That's showing you that if you have a sample like on a paint where you've got an orange peel, maybe you've got a plastic bag and you're trying to look for the direction of manufacture, the striations on the surface, something like that, you can see that in this illumination, in coaxial illumination. You're not going to see it in anything else. Even with severely oblique illumination, you're not going to see those scratches because they're so thin. Let's move up. The counterpart to coaxial is episcopic illumination when you go to the pole scope. This is the interior surface of a glass ampule, a glass vial, by oblique illumination. Change that over to coaxial illumination, and this is what you see, or excuse me, episcopic illumination. These circular features here are pits in the glass. You can see here a line of demarcation that is actual delamination of the glass. and you see what we believe are manufacturing marks in these linear parallel lines going across here. The only means of seeing this by light microscopy. Let's talk about some things that we can identify by PLM that we can't identify by infrared or even elemental analysis. First example is the infrared microscopy or spectroscopy of a cellulosic fiber. One is rayon, one is cotton. They both show that they're cellulose. Some slight differences here in this area, but in the world of unknowns, when you don't know how that particle has been manipulated or handled, that's not really enough to layer an identification on. So we can say it's cellulosic. This may not even be cotton. This could be a bast fiber, another type of bast fiber, for all we know. But you mount them up for polarized light microscopy, and you very easily can see that these are synthetic fibers. You can see the long striations in them, very typical of rayon. So between the polarized light microscopy and confirming by infrared spectroscopy that it is cellulose, you know that this is a rayon fiber. There's also some other polarized light microscopy techniques that you could use, refractive index and so on and so forth, where you could completely identify that if you have the microscopy skills to do that. Compare the rayon fiber, though, down here with this cotton fiber. This is obviously a natural fiber. You can see that it's very twisted and ribbon-like. This is uniquely cotton. If this were a linen fiber or jute or hemp or something, you'd have different kinds of physical characteristics. If this were paper, you wouldn't have this kind of twisting. You also probably would see bordered pits, so you could make some identifications there. But you certainly cannot do any of that with infrared data. Let's look at some EDS data. These are all silicon oxides. The first one over here has a trace amount of sodium and aluminum in it. Other than that, they're pretty much identical. These are all from different silicon oxide materials. By mounting them in for polarized light microscopy, it's very clear that this one is diatoms, this one is quartz, this one is silica gel. So your polarized light microscopy is going to augment your EDS data and give you much more specificity than you would be able to offer without it. You've got to use the right microscope. Here's a sample of it was a brown compressed pelleted material. So I took a little piece off of it, put it in water, and teased it apart to make this sample prep, put a cover slip on it, looked at it with the stereoscope. It doesn't tell me anything. I got brown schmaltz. But if I take that exact slide and look at it by polarized light microscopy, now not only do I have increased magnifications, I also have increased clarity in my optics. It's very easily seen that we've got all kinds of insect parts here. These are bits of antennae and hair, insect hairs and things like that. That's at 100x. We come over to 400x. Here is a moth or a butterfly scale. If you look down here in this location, we've got these hairs. That's a bat hair. All of this insect material, very little other material, and the bat hairs tells me that this is consistent with a bat guano. Something else that we can see through the use of light microscopy is we can look at, we don't only see that it's charred material, but we can see something about how it became charred and something about the nature of how it was charred. These two samples are obviously very different. This one doesn't have any, it's not round, it's kind of amorphous, it's got sharp edges, and it's not charred all the way through. We've got some of the material that's not even, doesn't show any browning or charring at all. Whereas this one has, if you look at it closely, around the edge you can see kind of a perimeter. That's where liquid has collected. This lacy area is where boiling has occurred, And this is a very characteristic center core area where you've had boiling. This particle was a spatter or a droplet of material that's either been on the surface for a very long time or an extremely hot surface so that it boiled very, very rapidly. Because of the opacity of that particle, you can't expect to get much in the way of originating material information through the infrared out of there. You can still mount particles if you want to look for inorganic materials, fillers and things like that, but you're not going to get any organic information from that that's terribly useful to determining origin. This particle, on the other hand, you can see some of it is charred, some of it isn't. These areas that are not charred are physically removed from a hot surface. So you don't have a lot of heat. Where you do have it, it's pretty intense because you melt and char here, but you still have areas that are unaffected. There's a heat sink effect of some type going on. Now, when you get ready to analyze this, there's several things that you can do. You can choose to analyze an area over here, so you can actually have 3 different zones in one sample. You've got your, shall we call it, virgin material, your relatively undamaged. You've got your more heavily damaged, and then in here you can see that there's almost a translucent brown. That's a zone where you can see it going from the colorless, getting gradually darker until you get over to the dark area. So you can sample that and do all 3 of those analyses on that one sample. This is another approach, is to go in and take a sample of the dark area and a separate sample of the unaffected, the virgin area, if you will, and cut out those samples and only do analyses on those. Let's talk about how to make a homogeneous sample from a heterogeneous material. I've already analyzed this sample, and this is clay, all of this fine brown particulate. We're looking at it in a polarized light microscope. It's mounted in 1662 refractive index liquid, and I've removed isolated samples of this material and prepped it for EDS and for infrared, and identified that as clay. It's an aluminosilicate clay. If I were to go in macroscopically, the chances of me picking up some of this clear potassium nitrate in conjunction with my clay is pretty high. So if I'm macroscopically creating an EDS sample or an infrared sample, I'm going to get a mixture of both. That simply makes your interpretation that much more difficult. So we want to isolate and analyze each sample independent from one another. To do this, remember I said this is in refractive index liquid. I'm going to show you a video where we slide the cover slip to the side. We use a tungsten needle to isolate the sample. We remove the refractive index liquid with amyl acetate, and then we mount the sample for analysis. So here we have our beryllium stub. Remember, these are about 1 millimeter by 1 millimeter square. So our samples are 150 micrometers in size. And you're looking at it with oblique illumination so that your sample looks white. Start the video. Here is our sample in refractive index liquid on a stereomicroscope, zooming in from about 10x to about 30x magnification. You can see here these larger colorless crystals are the potassium nitrate. This brown material is the clay. It's brown because of light diffraction coming from the transmitted light. Here you can see me pushing that cover slip to the left using my tungsten needle and exposing these particles of interest. Now I'm going to use my tungsten needle. You can see the liquid on there at the end. All I'm doing at this point is just grossly removing refractive index liquid and some of this extraneous particulate that I don't want to worry about. I just want to slide as much of the gross material away as I can. Now you can see I've identified that I've got a couple of those colorless particles actually on the edges here. So what I'm doing now is I'm using my tungsten needle to pull those potassium nitrate particles out and move them away. There we've got rid of them. Now we're going to bring in that micropipette tip with amyl acetate in it. We drop the amyl acetate on. We are still in transmitted illumination, so we can't really see our particles very well. I'm going to switch over to coaxial illumination. We can see our liquid much better. We can handle it. We can do some fine movement of that liquid. So I'm just doing some gross washing of this area. Let it dry a little bit. I'm going to come in. This is my particle that I'm going to work with. So I'm going to pull some of that amyl acetate off to allow that particle to dry a little more quickly. And you'll see that amyl acetate is drying, so we don't see that clay residue. Now we're going to come in and do a little more fine-tune washing. There's my amyl acetate, and I take my tungsten needle and wash that particle, run it over the top surface of that, and then I pull some of that amyl acetate away, which pulls away some of the remaining contaminating refractive index liquid. Now, to mount that, to pick that particle up, I want to use a little bit of organic adhesive. So I've smeared some organic adhesive here on a glass microscope slide. You're looking at it with coaxial illumination. You would never see it with oblique illumination. I've put about a 20 micron particle of that adhesive on the tip of my needle. Now we come back over to our slide. Here's our sample. We're using oblique illumination now, so our particle looks white instead of brown. There's my adhesive on the tip of my tungsten needle, and I pick that portion of that particle up that we want to look at. Now we're going to move that out. We're going to move in our beryllium stub. There it is in oblique illumination. Now we put it in coaxial illumination. We can see a lot better what we're doing. We add our micro droplet of amyl acetate. We put on our sample, and now we're going to pull some of that amyl acetate off because that's going to take with it a lot of the excess adhesive, so that when we analyze this, we don't have carbon and oxygen showing up quite as much from the adhesive. And that's your sample prepped. There's your sample prepped in oblique illumination. So that's ready for EDS. Let's make one for FTIR now. Here's a tablet. It's got a blue particle embedded in it. You see it here at 2 different magnifications. Higher magnification, you see that it's actually embedded under the surface. That can be important to know in the manufacturing process. Is it embedded or is it strictly impacted on the surface? Here's our sample that we've made our sample now. We've isolated, we've cut our sample, we've got it prepped for infrared. The sample we have is about 315 micrometers. This is on a potassium bromide salt plate being observed in oblique illumination. So let's watch that process. We'll start up here. We're just going to take another look at that particle in the surface. Because it's a tablet, I'm going to start out at least, and I'm going to add a little bit of water. That's our micropipette again, so we're adding a micro droplet of water to the surface. Let it sit for a minute or so. Come in with our tungsten needle and just start teasing through the water, teasing that surface material off of the particle, and eventually loosening that particle. In this case, that particle will float. We're not always that lucky. So we tease it a little bit, remove as much tablet material as we can, go in with a pair of our curved tweezers, pick that particle up, slide the tablet out, put in another clean glass microscope slide, turn on our coaxial illumination, adjust it properly, and you can see when we lay that down, there's still some tablet material on that. We want to get rid of that. So we're going to come in and we're going to do another wash of the isolated particle. Increase the volume, the ratio of the volume of water to the tablet material. Just kind of play with it a little bit with our tungsten needle. Bring it near the side of the droplet of water and just pull it out. I'm pulling the microscope slide to the left At the same time, I'm moving my particle to the right, so till I get it enough of it out here that I can grab that water under my tungsten needle and pull that to the side, taking contaminated water with it and also allowing this particle to dry. I'm rotating it because I know that I want it in this orientation for my correct hand positions for sampling that particle. No way we could analyze that particle whole. So there's my microscalpel. We're going to cut just a little small sample off the tip of that. We're going to save this for later in case we need it. I know that sample is way too large for what I'm aiming for, so we're going to cut off about 80% of that sample. We're going to take it and move it back over here, so we've got it to come back to later if we need it. Now what I'm going to do is I'm going to use my roller tool. Typically I want to go with the length of the particle. In this case, I know that's not really going to matter that much. I'm fairly certain I don't have different layers involved. So we're just going to go across it in an easy way for me to get to it with the roller tool. So there's our particle. Nice and flat. I know that that particle is down around the 5 to 10 micrometer thickness range, which is going to be perfect for our infrared analysis. We're going to pick that particle up. I'm going to move this slide out, and I'm going to bring in another slide that is holding my potassium bromide salt plate. I've gone back to coaxial illumination so that I can see a lot of the surface scratches and things here. We're going to lay our particle down. These surface scratches and this stuff makes no difference to what we're doing. It's not contamination. Now we're going to take one of our small cover slips and we're going to lay on the top of that. We're going to now take the tungsten carbide scribe, because it's got a tip on it that will grab a hold of that microscope slide, that glass, so that we can press down and pull that glass down, so that some samples will smear, other samples we just want to embed so the sample doesn't blow away. In this area you can see some of the small dark specks. At this point I don't know if that's contamination or not. I'll show you how we're going to get around that here in a second. But there we just scribe a box around it so that when we leave our microscope area to go to the instrument, we can find it. Here's what we're going to do. We've got a nickel A system so that we've got a rectangular masking system. So we're going to only analyze that area within the square box. That's what's nice about pressing this small particle out. We've got about 315 micrometers to work with in particle size here, so we can easily get a nice spectrum in that area right there. And in fact, our next slide, the blue is the spectrum of that exact particle that I ran, and the red at the bottom is the polypropylene library reference sample. Run through this real quick. I see we're getting a little bit low on time. This is a sample, and some of you may have already seen this. I use this demonstration a lot. Right here at the tip of the arrow, there is a faintly different colored red paint, slightly different colored than this. It was my job to determine if in fact that was real or whether it was just a color difference because of the black layer above it. So much too large to manipulate, so we've got to get that sample down smaller. So I used a microscalpel or a razor blade to make a very thin slice under that, make a very thin cross section with an emphasis on this kind of an area. I don't care about any of the rest of it. I just want to get an area like this. So I remove that area, take that to and I don't have images of this, take that to a clean glass slide, and I carve off everything, and I'll show you what my end product is here in a minute. I've got just a little bit of the black, come down, and I've got a little bit of the red. It's just right in this tip area. Everything else is carved away and thrown and put to the side. Then I take that piece and I roll with the length of it. If you roll with the length, and when I say length, I mean going with the layers, what happens is those layers will spread out and thin, and you can decrease the contamination across the, the smearing, if you will. So you can see pretty clear-cut areas here where you don't have any cross-contamination from one layer to another. Still not a very nice sample for infrared analysis. So I went one step further, carved out a rectangle in here, staying as close to the center as possible, carving out a rectangle over here in the dark red area, pressing them on KBR, producing these two samples. Again, this is in coaxial illumination because you can see all of the surface scratches on the KBR. We've got our red layer and what I call the plum layer. We run our infrared spectra of those two samples. You can see the circled areas where you're showing obvious differences, and I know that those differences are due to the red pigment used to create that color. So we've shown that we have a different layer. We've shown that it's due to the difference in the red pigment. So let's take a look and kind of recap what we've looked at. We've seen that just simply by looking at the sample, we can determine a lot more information about what is it we have. What is the true nature of that sample? We can't see that macroscopically. We get samples in here all the time when they say, identify this black particle. Well, it's probably not black. It's probably gray, or it's brown, or it's dark blue, or it's dark green. It's something other than what they think it is. We can create homogeneous samples from heterogeneous materials. I've shown you one technique. There's multiple techniques. Another one I did not have time to show you is using a solvent to extract a soluble material out of a particle. An example might be plasticizers from plastics. But anyhow, we can create those homogeneous samples and makes it much, much better for our interpretation. We're not trying to have multiple samples mixed together that we're trying to make sense out of. Slightly different than that is we simply have better preps for our instrumental analysis. Regardless of whether we've made them homogeneous or not, they're simply better preps. We get better data. In some samples, we can make a lot of identifications that cannot be made in any other way. They can't be made by infrared data or through EDS data. So it gives us some additional information. And finally, some problems are just solved through microscopic observation. You don't have to do anything else. It's all you need, and you're done. It's very quick and easy, and you're out of it. And sometimes you spend hours going through instrumental analysis when a simple microscopic exam would solve your problem. So that's where I'm going to stop. I've thrown a lot of material at you. We can take questions. One comment I do want to make is that I am a 66-year-old man with arthritis in my hands, and I can do this work. I did all of this analyses here. There's no reason why you youngsters out there can't do this work with a little bit of practice. So get out there and try it, and ask your questions.
All right, great. Thanks, Bill. Really interesting stuff there. Yeah, thanks for everybody attending today's webinar. And go ahead and in the questions box, type in your questions for Bill. Bill kind of answered the one that Jason posed early on in the presentation about how do you go about creating your own tungsten needles. And Bill referenced our website. There are a few places you can locate that. One is on Modern Microscopy, which is our online free journal, and there's a section in there called Prep School. So lots of sample prep tips, including tungsten needle making and sharpening, along with we have a YouTube channel, or also videos on our website. But you go to YouTube, type in Hooke College YouTube, and there's actually a video there. It's about 3 or 4 minutes on how to make a tungsten needle. So I see some of the questions are really starting to roll in here, Bill. Let's take a look at some of these.
Okay. Do you polish the cut pieces of KBR before use and after cutting from the larger pieces. Yeah, you start out with a large block of KBR, you cleave that into your small piece, and then you cut the small, or you polish that small piece. You can use water, ethanol, methanol as a liquid and polish it wet. You've got to be careful not to let it sit in one spot too long. Chantel wants to know what we use for as the organic adhesive. We use something called soluble gum that is not available publicly. We bought that years ago, and I don't believe that you can get it. You can use a rubber cement, anything like that that you pre-test. I think rubber cement, rubber cement is what we've used. We use that in some other applications. What if the blue particle is water soluble? Would you lose it? Yeah, Anne. That's a risk you take. You have to start somewhere. Generally, I can look at a particle and in most cases determine at least the class of what that particle is. This one, I was able to look at it and I knew that it was most likely a piece of plastic as opposed to a piece of sucrose, like a piece of lollipop or something like that that might be water soluble. Those are the chances you take. If you do that and you see it dissolving, you as quickly as possible try to remove that liquid or remove the particle. That's always a chance you take. Jan, do you prefer the roller and KBR plate above a diamond anvil, which is my favorite? Yeah, my basic problem is that, well, A, I haven't used a diamond anvil that much, but B, if you are subtracting out those bands in the diamond active region, it seems to me that they have to affect other bands that may be from your organic material. So we tend to use the KBR or the transmission as much as possible. Are tungsten needles ever reused? Yes. And is amyl acetate used? Yes. We typically use amyl acetate as a universal solvent. It does have good solubility properties, but the main thing it has is it has a good surface tension, so that when you apply it to a smooth surface, it wants to create a dome, a nice droplet that doesn't, if you put ethanol on a slide, it runs all over because it has no surface tension. Yes, and tungsten needles are reused. What I have is I've got a small jar. I've cut a circle out of the lid so that it's just a ring that goes on, that screws onto the jar, and I put a clean room wipe over that hole, and then I will use, I've got a larger bottle of amyl acetate that I'll wet that clean room wipe and then put my needle up and down in that. The one thing you do have to do is you have to have a separate needle for KBR and a separate needle for EDS. The reason for that is it's very, very, very difficult to remove KBR contamination from a tungsten needle. So you will often see KBR showing up in your EDS preps when it's not part of your sample and it's a little difficult to explain. KBR instead of sodium chloride. Don't know. I have used sodium chloride. It seems to me that it's a little more fragile. KBR is pretty much been what everybody in my experiential history has ever used. Sometimes I will use a compression cell and I'll use barium fluoride crystal. The problem with barium fluoride is that it has a very high cutoff wavelength. If you're really, really lucky, you can go down to maybe 750, 800 reciprocal centimeters. And I don't, to tell you the truth, I don't know, sodium chloride may be so soluble, may cloud more easily. I'm just not sure. Not a very satisfactory answer. Sorry, Jan. Linda says, how do you deal with static and keeping samples from jumping away? You pray a lot. There is something called, there's a gun that you can buy called a Zero-Stat. There's also some other tools that if I get particles in a plastic bag and I get particles in a Petri dish, sometimes I will zap it with that. Sometimes you have to resort to using a little bit of liquid, a little water or something like that in order to stabilize the particle. Difference between coaxial and oblique. Oblique light comes in from the side. It does not come in directly from the top. Oblique, it is a type of reflection, but it comes in at an angle from the side, whereas the coaxial comes in straight down from the top, hits the particle, and bounces straight up off of it instead of coming off at a reflected angle. Whitney wants to know, do you have a reference book you can recommend for trying to identify different fibers? Probably the best thing to do is if you can get your hands on some twig fecks, information for fiber identification. If you were to email Scott Stoffler at stoffler@macrone.com, Scott could help line you up with that. He's more in tune with the fiber literature. Hello, Troy. How you doing, buddy? What's the cost difference between standard stereo and coaxial? Don't know, Troy. I'll get back to you on that. I can tell you that my system is probably 25K. The stereoscope that you saw with all the whistles and bells. So you're probably adding another, I don't know, 8,000 to it or something for the coax. Pierce, can coaxial illumination be added to a scope in the field, or is it too difficult to do? That is a function of your scope. I don't know what brand scope you have. Any of the Olympus equipment, it's very simple. I believe any of it, it's fairly simple to retrofit. Some of the other brands may or may not be. One of the things you have to be careful of is if you're buying a what do I say? A more economical system, they may not be retrofittable. So you're just going to have to get back with your scope manufacturer and find out. And if they can do it, it's no big deal at all to do it. Yes, coaxial is much better than ring light. It's very different than ring light. It actually manipulates the light so that you can see things that you cannot see with ring light. So and that was from Jan. Anthony wants to know, how can I upgrade my stereoscope Leica MZ95 to coaxial? Not familiar specifically with that brand. I would get a hold of your Leica manufacturer, or you could get a hold of us here at Macrone, and we can probably give you some assistance on making the correct contacts for doing that.
Okay, I think that does it for the questions, Bill. We've answered quite a few, and also Bill's contact information is up on the screen. If you'd like to email him, feel free. We have another webinar coming up April 27th with Kent Rhodes of Macrone Associates, and he's going to discuss using XPS for industrial problem solving. And we hope to see you then for that webinar. And thanks again for attending today's webinar.